So in question 14, we've got someone playing billiards, and what they've done is that they've lined up a shot and they've hit the ball, and that ball has gone careening into the side of the pool table, hit it perpendicularly, and then bounced off. It came in at 2.1 metres per second and it went out at 2 metres per second. And we know the amount of time, somehow, that the ball remained in contact with the side of the table. And the question is, what is the average net force exerted on the ball by the side of the table? So here, let's just draw what we've got. So initially, we're going to have some side of a pool table, and we've got a billiard ball coming in with mass m, and it has a velocity that I'll call v0, so for initial velocity. So this is what things look like before collision. And then let's look at what's happening after the collision. So after the collision, we have exactly the same type of thing, except now that the ball is heading out in exactly the opposite direction instead. So it still has a mass of m, but now it's going out at a velocity v1. And we're told about these v1s and v0s. So let me just draw up the coordinate system. And we're told that the initial velocity of the ball, so initial velocity, and that's what I've called v0. Now, it seems to me that we're told the x component of this velocity, because you see we're given a scalar number. So I'm going to say that that's v0x is equal to 2.1 meters per second. And obviously, because I've defined the x direction to be this way, the y component of that initial velocity was just 0. And then the final velocity of the ball is going to be v1x, and now we're told that the final x component of its velocity was minus 2 meters per second. And since it went out in the same direction that it came in at, it came in along the x-axis and went out along the x-axis, just in opposite directions, then the y component of the final velocity has to be 0 as well. And what else do we know? We know that the velocity change took place over a very short period of time, and that was 3.3 milliseconds. So 3.3 times 10 to the negative 3 seconds. And the mass of the ball is m is equal to 0.38 kilograms. So what we need to do is to figure out the average net force that was acting on the ball during its collision with the side of the table. So I reckon to do that, we can probably use Newton's second law. So by Newton's second law, we're going to have that the x component of the net force. So it's going to be the x component of the average net force is equal to the mass of the ball times the x component of its average acceleration. And I suppose we're also going to have that the y component of the average net force is equal to the mass of the ball times the y component of the ball's average acceleration in the y component of the ball's average acceleration. And now luckily for us, we have a formula for the average acceleration of the object, which is going to be pretty handy because we know the initial velocity of the ball, we know the final velocity of the ball, and we also know the time period over which the change in velocity took place. So by the definition of average acceleration then, we have that the average acceleration in the x direction is, the x component of the average acceleration is just equal to the x component of the final velocity minus the x component of the initial velocity divided by the time. And similarly for the y component, but the y component is just 0. So if we now plug these two expressions for the average acceleration into here, so we can say that hence the average x component of the net force is equal to the mass of the ball times this acceleration and the average net force in the y direction then, since the average acceleration in the y direction was 0, then so too is the average net force. And so now that we have this expression, since we know this, and this, we can just go ahead and plug numbers in. And this is equal to, so the average net force in the x direction then is equal to the mass of the ball, which was 0.38 kilograms, multiplied by minus 2, minus 2.1, and then divided by the time over which that took place, and I get minus 472 newtons. So the question is asking us, what is the average net force magnitude and direction exerted on the ball by the cushion? Hence, average net force is just 472 newtons, and this minus sign here tells us that the average net force must have been in the negative x direction. So in the negative x direction. So probably for the purposes of putting this into Wiley plus, you would just need to enter this. So 472 with the minus sign.